Okay, so now let's look at implementing all of this, right? What does the interface look like? And this is typically the first step that you need whenever you go through the process of implementing logic, right? We want to have a traffic controller and we define its interface with the outside world, which is basically the set of inputs and the set of outputs. The first input is the clock, of course. We also have a reset signal, and we have these two buttons that pedestrians can press, right? The PED-NS and the PED-EW, corresponding to the north-south or east-west pedestrian crossing signals. Everything else, at least the way that we have defined it, is an output signal, and the convention we are going to follow is that the lights in the north-south are specified using a 3-bit value, right? Now you could argue that a 2-bit value is enough. I want either red or green or blue. To make life easy, we are basically going to have 3 separate signals, red, yellow and green, right? So that our encoding becomes 100 for red, 010 for yellow and 001 for green, right? As I said earlier, in the case of an FPGA, you have enough flip-flops that you probably are not going to miss this amount of logic, right? It's perfectly fine, and it makes some of your logic and implementation a bit easier. The danger with having a representation like this is that you could potentially have a scenario where both red and yellow or red, yellow, green, all 3 lights turn on at the same time, right, which is at least less likely if I had a separate encoding. I mean, I could still argue that 00, 01, 10, what do I do when I get a 11 signal, right? How does that get decoded? So the easier way is to say, okay, I have 3 separate bits and just somehow make sure that, or at least under normal logical conditions, at least I should never have more than one of them turning on. And if I do find that more than one turns on, it probably means something has gone wrong with the hardware itself. So we have 2 outputs like that, the north-south lights and the east-west lights. We also have 2 outputs corresponding to the walk signals for the pedestrian crossings. So this is what our interface looks like. Then comes the question of what should the rest of our code, the actual implementation, look like, and we will go through that in a lot of detail. Before we get into the actual implementation over here, we want to think about the strategy. How do we go about doing this? We first have the core FSM, right, the finite state machine that we want to implement. We can already know that we need a state register with reset, some kind of next state logic and an output decoder. But as we already saw, this particular finite state machine also requires some kind of timer integration, right? There is a concept of timeouts that we need to implement. Some kind of configurable counters and implementing this timeouts needs to be handled carefully within the logic that we write. Now how do we handle pedestrians? There is one particular concept over here which relates to the fact that we are getting inputs from the outside world. A person presses a button, there is a possibility that that input signal is not synchronized with the clock that we have, right? And in particular, there is a problem of something called bouncing, where when you press a mechanical switch, it actually tends to sort of make the contact, then break, make, break, make multiple times, all in the period of maybe around 10 to 20 milliseconds or so. So it's like too fast for a person to really make out that this is happening multiple times, but well, 10 milliseconds on a 100 megahertz clock is many thousands, possibly millions of clock cycles, right, close to a million clock cycles. Right? So it's not something that you really want to just dismiss out of hand and say, okay, this is not going to happen, right? What we would like is there some way by which I can actually make sure that even if I have a simple problem of this sort where there is a button that's sort of jittering or vibrating or causing multiple make break connections over a short amount of time, is there some way that I can actually detect that it was a button press? So we'll look at one possible example of that in the code that we write, basically where we are going to be latching the request into an internal set of registers and then making use of it. We also need to implement some kind of timing for the walk signal. This will actually not be implemented in the code that we show, but these are all sort of enhancements that we might want to add on. There are also a few things like safety mechanisms. What kind of state encoding are we using and whether it's safe? How are we going to implement timeouts? Can we implement a test bench where we verify the outputs and so on, right? All of these are things that potentially should go either as part of the design or definitely part of the test bench. Now the test bench basically leads us to this whole idea of what is our verification approach, right? When we write code, we should have some way of sort of stating upfront how we are going to test whether it works the way that we expect it to. Which means of course that we need to know what kind of basic functionality is expected of this system, what are the state transitions, what are the light sequences, what are the timing requirements, how do we test these, right? So we are going to come up with a few test cases that exercise all of those conditions. Ideally, we should be able to look for some kind of corner cases. For example, what happens if the walk button is pressed multiple times, right? What should be the behavior? Well, we have to decide one way or the other. The most likely behavior is from the first time that it is pressed, right, you automatically move into the sort of going into yellow and then going into the walk signal mode. But what happens if within that time the person just goes and keeps on pressing the button multiple times very quickly, right? We could argue that okay, I am just going to handle it corresponding to the first one and ignore everything else, or I might decide that I actually want to generate another signal that basically tells the person stop, this has already been pressed, now stop pressing the button again. Or I might decide that maybe this indicates some kind of urgency, and based on that maybe I need to shorten the time that I am actually going to have for a yellow. So these are all again functional requirements, but the point is you need to know how you are going to handle it and have test cases that actually check for something like that. Once again, some kind of minimum timing checks. Are you able to ensure that each of the signals is on for a certain amount of time before you turn it off? Safety checks, ensuring that there are no conflicting greens. You cannot have green on both the north, south and east, west at the same time. There should be a certain amount of time for which there is an all red signal. The yellow timings should be fixed and so on. Now all of these are things that we will consider in the test bench that we look at to varying degrees. There is also a concept called fault injection where we can actually try and imitate the presence of certain kinds of faults, right? For example, what happens if a button gets stuck, or what happens if the clock stops, or what happens if maybe due to a lightning strike or something else we end up in an invalid state. How is the system going to respond and how is it going to come out of that? The question becomes, how do I even force such a scenario? For example, how do I force the system to go into an invalid state, because no set of known inputs is going to send it to an invalid state. So I should be able to sort of inject a fault where I say that directly one particular value inside a register gets set. I can do such things in a test bench. I can sort of forcibly override the value of a particular register and then see how it behaves from there on. So all of these are different aspects of verification. What we are going to do now is look at a very small subset of these as a set of illustrative examples. Alright, so I am not showing this on EDA Playground also, although we will sort of be having the code on EDA Playground as well. It is something that you can examine and try and go over on your own. In this particular case, I am actually running the code directly on a system. This is a Linux based system in a virtual machine where it is possible to sort of run the compilers and so on and directly make edits and run them much more conveniently. I would strongly recommend that all of you try this out, try and get hold of either a Linux machine or a Linux virtual machine. If you have a Windows based system, the WSL, the Windows subsystem for Linux, is a very good way of doing that. If you have a Mac, then most of these tools actually run pretty much natively on Mac. They can be made to compile and run. So all of those are possibilities, and I would strongly recommend that you explore a little bit about how to do that. If for whatever reason you are unable to install this software on your systems, then EDA Playground still gives you a lot of flexibility in terms of the things that you can try. Alright, what I am going to do over here is actually open the code and sort of walk through it in a little bit of detail. Now we already saw that the interface, right, essentially the inputs that we have over here are defined like this, right? We have a certain number of inputs, we have a certain set of outputs. But as you can see over here, I have defined a few timing parameters as well, right? Now one thing you might notice is this time scale that I have given at the top, right, is in milliseconds, and that's just because I plan to sort of use this with a 100 Hz clock, right, and it sort of makes it easier for me to just work with everything in the order of milliseconds, right, rather than trying to define it in terms of nanoseconds and 100 megahertz and so on. the numbers that we are talking about start to become a bit easier to understand. So, at a 100 Hertz clock, for example, if I count for 1000 clock cycles, right, that basically corresponds to 10 seconds. So, it makes it easy for me to have sort of logical numbers to think about over here. Now, in practice, you might actually be dealing with a 100 megahertz clock, in which case this might actually correspond to a basically 10 power 9, right, that you need to count in order to implement 10 seconds, right. It's doable, and that is in fact quite easy for a piece of hardware to do, right. It's not as though implementing a counter up to 10 power 9 is very difficult. It basically means a 32-bit counter or a 30-bit counter, right, which is not a whole lot of hardware. So, if you need to, you can do it, right. But we are keeping things simple out here, and therefore, I am saying that the east-west green time, as you can see, is a smaller quantity. It's 500 counts, that is basically 5 seconds, and the reason is because north-south is presumably the more important road. I have a yellow time which is 3 seconds, right, and I have a red time which is basically 1 second all red, and the walk time in any direction is basically going to be 7 seconds. These are just numbers I have chosen. You might also notice that I do not have parameters such as minimum green time and the green red overlap or something of that sort. There could be a few more timing parameters that get added in. As I said, not everything that was discussed as potential requirements of the circuit has been implemented over here. I am implementing sort of a subset of functionality, right. Okay, so now how do we go about implementing our logic? We already know what the design looks like. It was basically a 6-state finite state machine, and this is pretty much implementing the same thing, right. We have an NS green, NS yellow, all red 1, EW green, EW yellow, all red 2. And as you can see, because I have defined it as an enumerated data type, I have not specified NS green equal to 000 or anything, right. I mean, I am just letting the compiler sort of decide what these values should be. It is an enumerated data type. Most likely it will start out by assigning 0 to the value NS green and then going 1, 2, 3, 4, 5 to the others, but we do not care, right. We are perfectly fine with the state machine synthesis system just assigning whatever numbers are required over here and choosing it in a way that makes the implementation more efficient. Now, keep in mind that as far as simulation is concerned, none of that happens. In simulation, it just keeps it as 000, 001 and so on, right. It does not do the sort of state assignment optimization and so on unless we actually go for synthesis of the resulting circuit. Okay, so we have a state T state and next state. So, previously we talked about a current underscore state and next underscore state. This is also common to just call it state, right. I do not necessarily need to have it current underscore state. You might also have something which basically says something FSM underscore CS to indicate current state and FSM underscore NS for next state. There are lots of different conventions that are followed, right. Most of them are fairly obvious when you look at the code. What is important is that you recognize the patterns rather than going by the specific names that are used. Now, one thing over here you will notice is that I am defining a variable called the timer count, which is a 32-bit value. It is not clear whether I actually need a 32-bit value, but we are just using that over here because these numbers that I am dealing with 1000 and so on, I most likely do not need a 32-bit value, but well, no harm done, right. I might as well put it in there and see what happens. What is interesting is these 3 signals, timer count, timer done and current timeout, are going to be used to actually implement our timeout logic. Now, this set of signals, right, the sync1, sync2, pressed and so on, right, are used for a very specific purpose. It is basically used for synchronizing the external inputs, which in this case are the PED-NS and PED-EW, right. These are the external inputs. I am going to synchronize them using the sync1, sync2 and the pressed signal. Now, I am going to be explaining a little bit about how this works. You could implement something even just ignoring all of this, right, and you would have a functionally correct system. So, the reason I am bringing this in here is to sort of indicate a potential issue that is very often addressed by finite state machines, which is basically how do I synchronize an external input. So, now let us get to the logic, right. So far it was all declaring our signals and so on. Now let us get to the actual logic, right. The timer logic basically just has a always block of its own. it is a flip-flop, right, a set of registers, and what we say is, as you can see, the way that I have written this code is, it is always at posage clock, but the first condition is if not reset underscore n. This, as we know, is a synchronous reset, right. Basically what it says is, I require the clock signal in order to reset, and it is also an active low reset, meaning that when reset underscore n has the value 0, not reset underscore n has the value 1, which means this if condition gets triggered and timer count gets set to 0. Now, if that is not the case, the next thing that we check is, if timer done, then timer count becomes equal to 0. Now, what is timer done? Well, we will have to figure out some logic that tells us when to reset the timer, right. Now, why is this an issue? Because we would like to have different timer counts, right, such as 1000 cycles for the green time, 700 counts for the walk time, and so on, right. And the way that I am doing it is, I am going to basically have one extra piece of logic down here on line 53 that says, if timer count is greater than or equal to current timeout minus 1, right. So, let us say that let us say current timeout is set to 1000. If timer count becomes greater than or equal to 999, in other words it becomes equal to 999, the timer done signal will become 1 and timer count will become equal to 0, right. So, by putting in a logic like this, and if I somehow figure out how to set current timeout to be 1000, it means that this entire logic out here is going to count from 0 up to 999 and then go back to 0 and count again, okay. And that is nice, because basically what it means is, just by changing this value that is present in current timeout, I can change the behavior of this timer logic. By setting current timeout to 700, for example, I can make this count for 7 seconds. By setting current timeout to be 1000, I can make it count for 10 seconds. And this timer done signal is a nice input that I can use to do my state transitions. Okay, so far so good. The next thing is this slightly complicated piece of code, which is basically input synchronization and edge detection. For the time being, if you find this confusing, feel free to sort of skip over this part. I am going to go ahead and explain it anyway, but it is good to know about it, but it is not the most important part of this entire design. What we are saying in this part is, this signal, the ped underscore ns, is an external signal. It could get pressed at any point in time, which may not have anything to do with our clock signal. So, why is that a problem? I could potentially even have something called metastability, which is basically saying that the ped ns comes very close or within the setup time window of my clock signal, and as a result, if I directly look at ped ns in my state transitions, there is a chance that I end up in an unknown state, because I did not know whether this was supposed to be a 0 or a 1. Okay. I want to avoid that, and therefore I use something called a synchronization circuit. First things first, what happens in a synchronization circuit? I bring in two temporary signals. Let us just talk about ns for now, right, the north-south, the east-west is exactly the same. These two, sync 1 and sync 2, are just dummy signals in some sense, right, and the ped ns pressed is essentially going to be our synchronized version of the ped ns signal, right. The user only gets to interact with ped ns. You press a button, it activates ped ns. What happens over here, this logic basically is continuously taking the current value of ped ns and putting it into sync 1, taking the value that was in sync 1 and putting it into sync 2. So, this is like a two-stage shift register, right. Now, why is that useful? Because it basically says that even if ped ns for whatever reason was, let us say, had a setup violation, it ended up somehow clocking very close and changing very close to the clock edge, that might mess up my sync 1, but the sync 1 is then feeding into sync 2. The transition on sync 1 is not going to happen at exactly the same time and not within the setup window of sync 2, which means that sync 2 at least is not going to go metastable. It is going to be in either a 0 or a 1 state, which is at least a known state, and eventually, right, I will find that this ped ns, hopefully I have pressed it for long enough and my clock signal is also fast enough that it actually picks up a value which is not exactly at the within the setup hold capture window, right, and eventually it comes down to the fact that the correct value of pedns gets stored into sync1 and the value of sync1 goes into sync2. Alright, so far so good. Now we have something called edge detection. Look at this logic. What it says is, I will check whether sync2 has the value 1 and the pedns pressed, which I have not defined so far, has the value 0. Okay, in other words, I have not so far indicated that I have pressed the button, and also I am not already currently in a walking, the walking mode for the north-south signal, right? If I am already in the walking mode for north-south signal and somebody comes and presses the button, I shouldn't do anything pretty much, right? But what I am going to do is, if this case is there, that is to say my sync2 signal, that is after synchronization and going through two stages of synchronization, if my signal has become 1 and I am not currently already activated the pressed button and I am not already in the walking mode, then set pedns press to 1. That is basically, this is a synchronized signal that is looking for a specific edge. I am not already in the pressed mode and I have a signal from the external input that has become equal to 1. Okay. Interestingly, what happens over here is this becomes 1 over here, and then afterwards it checks if there is a clear pedns signal, it sets pedns pressed back to 0, right. So this is an interesting set of transitions. We need to think about where clear pedns signal comes from. That's going to be from one of the states, right. What about walk ns? That's also going to be from one of the states. So basically, in other words, what this pedns pressed is doing is, it's a cleaned up version of whatever we got from the outside world, which also makes sure that we are not currently in a walking state, and then sort of turns on the walk request, right, walk pending request. Exactly the same thing is also done for the east-west line. So effectively, if you want to sort of summarize what is happening in this always block, the pedns pressed signal is going to become 1 when I am currently not in a walking mode and I press a walk signal asking to go in the north-south direction. PedEW will be 1 when I am currently not in already walking, allowing a east-west walk, right, which would be the case, if I am already in the east-west walk mode. I would allow it to basically turn on the PedEW pressed, and this would be a cleaned up version of the request signal, which means that after I have done all of this cleanup, from this point onwards I can just look at pedns pressed and PedEW pressed as my actual logic that needs to go into my FSM. Okay, great. Now that slightly confusing bit of logic is out of the way, let's look at the actual FSM itself, right. As we said earlier, right, we have a state register update, which is very simple. It basically says at passage clock, by default go into the NS green state. Now this is arguable, right. You might say that, hey, this was a bad state to go into, maybe I should go into the all red 2 state, right, and that probably makes a little bit more sense, right, because what it says is all red 2 will remain in all red 2 for a small amount of time, 1 second or so, and then go to NS green, right, which means that yes, it is now getting back into normal operation. Now the reason why in this case it probably is okay is that in any case when you have NS green, the rest of the logic also ensures that everything else is sort of turned off, right, or there are no other signals. But you could argue that this was not a good decision, right. I am going to leave that. If you wanted to make sure that that was not a good decision, the simple way to do it is modify your test bench so that it adds a check saying that after reset you should come up in all red. That's a nice way of specifying to the designer that you want the reset condition to be all red, because only by bringing it up in all red will they pass that test case. We will look at test cases in a moment. What does the next state logic look like? Default assignments next state is equal to the present state, it is not changing. Current timeout is equal to the NS green time, right. So basically because we start out in the NS green state, the current timeout is also set to NS green time, and if we don't know anything else about it, basically that's what the current timeout is going to be, right. Think back about what current timeout does. It basically says I'll keep on checking the timer count as soon as it goes beyond current timeout minus 1, the timer done signal will become active, and of course the timer itself will also get reset back to 0. Clear ped ns is 0. Where was clear ped ns used? It was basically used in order to push this signal back to a known state, right? But in any case, we have this thing that when I come out of reset ped ns pressed and ped EW pressed are both 0. So I don't really need to change the clear ped ns value. Now let's look at the state transitions, right? What it says is, if I am in the ns green state, my current timeout should be set to ns green always. I can keep having this over here. It's a nice way of making sure that I actually in each state specify what the timeout should be. But now what it says is, let's say that the timer is done or there is a request to walk east-west. Notice that I am not just using the ped EW signal, I am using the ped EW pressed. If you go back and look at this logic, what that means is ped EW pressed is going to take a couple of cycles after ped EW to actually make ped EW pressed equal to 1, right? Now you might argue, hey, isn't that a bit of a delay? Well, it's a 2 millisecond delay, right? Even at this 100 hertz clock, well, a 0.2 millisecond or 20 millisecond delay, right, on a 100 hertz clock. Probably not enough to worry about, and it allows us to ensure that we don't have setup hold problems on that particular flip-flop. So in a lot of cases, this kind of synchronization delay is usually considered acceptable and preferable rather than having metastability. So in this case, what we are saying is, I actually check the ped EW pressed signal and not the raw ped EW signal. But if either one of these conditions is satisfied, right, either somebody wanted to cross or it timed out of the green, I go to yellow and I clear the ped EW signal if it was set earlier, right, because I know that it has been pressed. I can know that I need to clear it before I get to this state. Now I go into NSW, right, it basically sets the current timeout to yellow time. What that means is, it will remain in this state by default for whatever is the yellow time, which I think was 5 seconds, right, 500 counts. It will remain over there until that counter, timer count, exceeds 499, right, and then timer done will become equal to 1. Next state will become all red, and when I go into all red, current timeout will change, right, and your timer count, by the way, would have got reset to 0 and will once again start counting up from 0. So the transition looks fairly simple, right? If timer done or ped EW pressed, go to NS yellow. In NS yellow, just wait, right? Don't do anything, don't jump out of it. Wait for the timer to time out, go to all red. Once again, just wait for the timer, go to EW green. Here in EW green, again I need to sort of look for either timer done or the ped NS pressed. Maybe somebody wants to cross in the north-south direction. Go to the EW yellow signal, right, and clear that north-south signal if it had been set. If it was timed out, then clear ped NS is actually unnecessary, but it does not matter, it is safe to sort of clear it anyway. Right. Go to EW, wait for timer done, go to all red 2, go to all red 2, wait for timer done, go back to NS green. And in this case, as you can see, my default state is set to NS green. As I said, this is debatable. You might say that maybe the safe choice would have been all red 2, right, but okay, we have made this choice. As I said, if you as a designer did not want this to happen, make that as part of the specification and also add a test case to ensure that after reset it comes up in the correct state. Next state logic is taken care of. Now let's look at the output logic, right, which is also fairly straightforward. By default, everything is red, okay, but if you are in the NS green state, lights NS become 0, 0, 1, which is basically green on the north-south direction, and walk NS will become 1 if there are no new requests for pedestrian crossing, okay. In the yellow direction, or when you go into the NS yellow state, it becomes 0, 1, 0, and the all red 1 and all red 2, I am combining them together over here, I am being lazy, right, and basically saying that, yeah, by default anyway it sets to 1, 0, 0, so I do not really need to write that code over here, okay. Now this is okay for simple scenarios, but in many cases it's actually cleaner and a better way of writing code to actually make it explicit over here exactly what the values should be rather than relying on these defaults, right. Similarly, we have EW green and EW yellow to handle the remaining output conditions.